actual object, but rather is an interpretation of the gray levels in the image. Of course, the image came through as varying levels of gray. Actually, I believe it's 256 levels that can. A couple of other books or papers that have been done on this subject. This one is called The Martian Enigmas, and it is a marvelous collection of the very best images of this material that has ever been published. It's by Dr. Mark J. Carlotto, who is an image processing engineer, a PhD with many, many peer-reviewed articles to his credit in the field of applied optics and image processing. And he is still an active researcher, having begun working on this topic since 1987 or so. And I have another paper here, which I'll explain later, but it is by that same Dr. Horace Crater, whom Ananda gave you a quote from earlier, although those who came in a little bit late didn't hear it. Are some very interesting objects. They're small, they're very bright, and they look like little mounds about 100 feet high, and they're very uniform. It's been proposed that geometric regularity, some kind of geometric grid, would be a way of possibly finding signs of intentional design. This has been put forward by a number of scientists, not just Mars enthusiasts. If you could make measurements from uniform-sized objects, and they're small, so that you know about exactly where the center of them is, you can get a more reliable kind of geometry that could be evaluated, perhaps. So Dr. Horace Crater of the University of Tennessee Space Institute began a research project on that back about 2 years ago, and it finally took the form of a rather lengthy paper called Mound Configurations on the Martian Cydonia Plane, a Geometric and Probabilistic Analysis. And I'm pleased to say, and proud to say, that it's signed Horace W. Crater, the University of Tennessee Space Institute, and Stanley V. McDaniel from Sonoma State University, because I helped Dr. Crater to some degree, a small part of it, but I did sign on to the project, and I have some comments in here myself. So here's A and D and E. This down here is B, and this one up here is G. So the first thing that was found was that this particular group makes a very close to isosceles triangle, which is a triangle with two angles the same. And the two similar angles are these two, which we labeled R, and we labeled this one L, and so we called it an LRR triangle. And I hope this doesn't get too math sounding, but I'll do the best I can. But this was called an LRR isosceles triangle. And the question is, how closely does a perfect LRR triangle fit on the mounds? So Dr. Crater developed a method of testing that. We'll see it in a moment. But he then measured from here to here, and we found a right triangle. And so we have an isosceles triangle butted up against a right triangle, and it's done in such a way that something unusual happens. The triangle formed by AEG is a right triangle, and the triangle formed inside of this by GDA is also a right triangle. The 90-degree angle is here, and they both have the same angles. So they're what we call in math and geometry similar triangles, where similar means specifically they contain exactly the same angles. So now we have another ideal figure. The mounds aren't quite in the right place. How close does this ideal geometric figure fit the mounds? We've called this the pentad, GABDE, because we have GABDE. So that's what we call this structure. What we're going to start showing you is tetrahedral geometry, or the geometric characteristics of a tetrahedron, because that's what we found here. So we're looking in the mound configuration at structures or angles that fit inside of a tetrahedron. The question is, how closely do the mounds actually fit this ideal geometric figure that contains the angles of a tetrahedron inside of it? There's three right, well actually there are four, but there are three right triangles here that are identical. That means the same size as well as the same angles. This begins to look like something that we should apply probability to see if it's likely that that could occur by chance. So we call this the hexad, because there's 6 mounds involved. Here we've shaded this one is also there, and this one. All three of those are identical. But does it fit? I hope I've got the slide where it shows you that it fits. Let me tell you in advance, it fits with extreme degree of precision. It's very tight. Dr. Crater developed mathematical methods of testing the fit, and the degree of fit is very, very precise toward the estimated centers of the mounds. In other words, the vertices, or the points where the lines meet on this general figure, fit on the mounds toward the center very closely. We then discovered, and this was my contribution to the paper, I was the one who found this. I was looking at this pentad figure, which you see here in the bold lines, and all of a sudden my eye, which by the way is trained to see things in diagrammatic form, because of my training as a philosopher, I often represent in teaching things by using diagrams. So I'm very familiar with that, and my eye caused me to jump into this rectangle here. And there are no mounds at those points, but I started exploring the nature of that rectangle. It represents what's called a square root 2 rectangle. The short side, if it's counted as 1, then the long side is equal to the square root of 2, or 1.414. The pentad of mounds is such that 5 of the mounds fit precisely on 5 of the corners and midpoints of the larger figure, the square root 2 rectangle. Furthermore, when we include the hexad out to this mound here, it fits on a corner point of a larger square root 2 rectangle. And it happens that the orientation of this grid, this angle of the orientation, matches the angle of orientation of many, many figures, including the face, the fort, and some of these pyramidal shapes here, which in itself is of some interest. What's also of interest is that Dr. Crater then calculated the probabilities. He ran 200 million computer simulations or models of distributions of 5 mounds, where the computer was throwing the mounds out at random on an equivalent area, and the mounds that it was throwing out were the average size of the mounds here, so that it was all very similar in character. And after 200 million throws, there was not one single duplication within the degree of precision of this figure. With very deliberate and careful mathematical calculation, he concluded that the chances of this figure of mounds being caused by random forces was over 200 million to 1, against its being formed by random forces. Then he decided to include all of the mounds in the entire area, with the exception of 4 here that are too close together to measure properly. So he included a total of 12 mounds, which are all the remaining ones, including the original ones. And he used another method, which is a good scientific procedure. And he calculated what's called the standard deviation, or a z-score it's called. The anomaly is what they call almost 5 standard deviations away from the expected norm. And according to Dr. Crater, who is a professor of physics at the University of Tennessee Space Institute, this almost 5 standard deviations is so far beyond the possibility of chance that it is virtually impossible that these mounds are the result of chance random distribution. Now that is a piece of information that is independent of the issue of whether the face is artificial. It is of objects in the area of the face, which tends to suggest the face is in a context of extremely anomalous structures. In terrestrial architectural tradition, the square root 2 rectangle was one of several figures that were used to express what they felt was aesthetically pleasing in proportion. And also, it's been proposed by a researcher here in England, John Legone, who is an Egyptologist, that the layout of the pyramids at Giza was developed the way that they are set with relation to one another, so that they're within a rectangle that is square root 2 on one side and square root 3 on the other, and square root 5 on the diagonal, and that was developed architecturally by first inscribing or laying out a square on the ground and then taking its diagonal as the side, because the diagonal of a square is the square root of 2. And as you know, the square root of 2 is what they call an irrational number, so it isn't easy to calculate, but you can calculate it very easily by drawing a square. And then its diagonal is square root of 2 as compared with the side of the square. So it was used by architects to develop these proportions simply by starting with a square. And if you start with a square and then you generate this from it, you can then from that generate square root 3 rectangle and square root 5 rectangle, and all of those were in use architecturally up into the Middle Ages and considered to be highly aesthetic, if not even symbolic in their nature. So we have here a geometric pattern in a grid that's almost virtually impossible that it could have been random, and it has a cultural meaning, and it also has a geometric meaning because it reflects the geometry within the tetrahedron. So this seems to be an extremely powerful reason for looking closely up there and seeing what on Earth, what on Mars is going on. Now, it doesn't prove that these mounds are artificial to say that they are not randomly placed. There are geological laws that produce some kinds of regular geometric patterns on the Earth. For example, mud will crack in a hexagonal form. But we know of no geometric rules or laws that would produce this kind of regularity in a series of mounds. And as far as we've been able to find out, no geology does do so. So these are highly enigmatic and require research.